Is it recording?
Yes.
Good. So again, I invite people to ask questions during the talk and not wait until the end. It's supposed to be interactive. I don't know whether I talked a little bit about Alice last time, but just to point you to it, this is an organization that is the European Lab for Learning and Intelligent Systems that tries to connect in a network sort of the machine learning community. So Lenka is part of it, I'm part of it. And so it's also to exchange students between these institutions. So if you're aware of this, you could talk to your supervisor to see if you could get exchanged with another lab in Europe. Just be aware that that thing exists and maybe look it up on the internet.
Oh, I saw it just earlier, and I think if there is, I think maybe that's it for this class.
Okay, good. Okay, I will talk about symmetries in deep learning. And so first I'll give us a quick introduction. I'll give a little bit of some background in deep learning. I'm not sure how useful that is in this crowd, but let me do it anyway to at least set the stage. I'll talk about graph neural networks. I'll talk about natural graph neural networks, which is very recent work with Pim de Haan and Taco Cohen. I'll talk about group convolutions, gauge convolutions on meshes. And then if there is time, we could go into some recent work on SE3 transformers, which is basically a mixture. It's a graph neural net that also transforms equivariantly under geometric sort of spatial transformations. And then I have one slide on how equivariance can also be used in reinforcement learning. Can everybody hear me in the back fine? Or yeah? Okay, good. So what is geometric deep learning? So actually the Alice unit in Amsterdam has its core topic geometric deep learning. Michael Bronstein is also part of that Alice program. And geometric deep learning is deep learning on data which is not in a Euclidean space. So we are used to applying deep learning to first speech, right, on our phone, speech recognition, that's one-dimensional signal. Then came images, a two-dimensional signal. MRI data, that's a three-dimensional signal. And perhaps fMRI data could be a four-dimensional signal. But it's all like a regular gridded signal on a Euclidean space. And CNNs, particular convolutional neural networks, work excessively good in this particular domain. However, what do you do when the data is on a sphere? So what if you want to study the sort of weather patterns on the Earth, or maybe sort of storms where they appear on the Earth? Or what if you wanted to study social networks, which is just a graph? It's not so obvious how to immediately apply deep learning to these domains, and this is what this lecture will be about. And you can sort of try to remember it as 4Gs, geometric graph, group, and gauge convolutions. And we'll talk about most of those today.
So, what was special about the Euclidean space? What was used in the Euclidean space that is so special?
Why Euclidean space is special?
In this use, not in general, in machine learning. What are the features of Euclidean space that convolutional networks use that would be different than different manifolds?
Well, so let's go back to the basics. So most people basically pre-process their data in features, and then they just apply let's say, some kernel machine or an MLP, multi-layer perceptual neural network, to those pre-processed data. That's sort of the classical way of doing things. So then came sort of convolutional neural networks that recognize that if your data is in some sort of flat Euclidean space, that you could apply, that there is this concept of translation invariance. In some sense, it didn't matter whether you detect a person on the left-hand side of your image or the right-hand side of the image. That idea basically gave rise to convolutional neural networks. And that is a huge savings on the number of parameters, and it also implements the right inductive bias. And so these convolutional neural networks are really working extremely well in these sort of domains where you have this sort of stationarity or this kind of if you want this kind of translation invariance.
But this has nothing to do with Euclideanity.
No, that's maybe true, but so then the next question becomes, what if the data doesn't live on a Euclidean space, right? So what if the sphere is clearly non-Euclidean, right? So or a graph. So people had these data sets, and you make a transition from pre-processed data to raw data. So that's a step, and then the next step is to say, okay, what is the symmetry group that's underlying your data? So, and I guess the translation symmetry is related to Euclideanity in some sense, because I mean, I guess you could do, and that's something that happens in this talk, you could do harmonic analysis on non-Euclidean spaces, but I wouldn't call that necessarily translation invariance. You know, on a sphere, it's clearly no longer a translation, right? It's much more, it's a rotation in this space. So, so it is the generalization of what, you know, ordinary the translation group is to harmonic analysis in more sort of complicated spaces in some sense, and in a way also arbitrary curvature spaces. Yeah, so there is actually a lot of application areas out there. The ones that I find most interesting at this point in time is chemistry and biology, and perhaps medicine, where you'd study molecules, you study, let's say, properties of molecules. We actually started to apply this to, let's say, predicting how well a particular medicine, a particular molecule would respond to, say, a COVID infection, how much it could sort of suppress a COVID infection. And so you can use databases of billions of these molecules for which people recorded some properties, and you can try to generalize across this entire database which of these molecules would actually bind well to certain ligands, which would then suppress the infection. And okay, so that more generally, material sciences and designing new materials, this type of work is very relevant for. Okay, so this is a physics crowd. So let's go back to maybe the most famous physicist of all, sort of Albert Einstein. And so clearly in physics, symmetry plays an absolutely crucial role. And maybe to give you two examples, but maybe the most important idea is that if you write down your equations, you should be able to write them down covariantly, which basically means if I transform to another frame of reference, let's say a different observer, then my equations should transform in a very simple way, right? I should be able to just transform the vectors and the tensors and whatever that are underlying my equations. I should be able to transform them to this new space in a simple way. And this led, for instance, Maxwell to basically to the insight that the electric field and the magnetic field are just two sides of the same coin. It's exactly the same phenomenon, but observed by two different observers, one that is flying with a certain speed relative to the other observer, right? So the electric field for one observer that's standing still would be a magnetic field for another observer, which would fly past that with a certain speed. And so the Lorentz transformations, which underlie special relativity, are basically the symmetry group of these of this sort of electromagnetic theory, and where people used to write things down in terms of two fields, electric fields and magnetic fields. You know, I guess this is still written like that, but you could also write things down in terms of sort of more general objects which transform properly. And then, of course, so that's how, you know, symmetry, the Lorentz symmetries act, let's say, on electromagnetism. And one step further, you could go and say, well, actually, gravity and acceleration are also related to each other by a symmetry transformation. So if I take an observer which accelerates relative to another observer, then where one observer would interpret what's happening perhaps as gravity, the other one would interpret something as acceleration. And if you're in a closed, sort of small chamber, you would not be able to tell the difference between those two things. And that insight, namely sort of covariance or under sort of accelerated frames, gives rise to the whole theory of general relativity. and to the idea that masses curve the sort of the gravity field, and et cetera, et cetera. So it's an extremely powerful principle that even underlies the most basic of all theories, perhaps, which is the standard model, where there is 3 symmetry groups that underlie the transform particles into each other under these sort of symmetry groups, and give rise to these gauge bosons as well. Anyway, so how is that at all related to deep learning, one could ask. Let me give you a quick introduction of deep learning so we're on the same page. So you can take an input image, it's a two-dimensional image, and you could define a convolution. So let me first show you a convolution. So here is an input image, and here is sort of some kind of convolution, which is where you slide the filter that you have over the image, and you sort of filter there with the image. This is an edge detector, and sort of you get one filtered image like that. Then there's operations like pooling, which downsample the image, let's say by a factor of 2 in both directions. And then there is nonlinearities which you apply, which are of different forms. This is a ReLU, and then we have a leaky ReLU, a PReLU, and then you have a randomized ReLU. There's all sorts of nonlinearities, sigmoids, tanh, 1080s, etc., etc. So that's the basic operation, a convolution. And you apply this multiple times. So you apply it with one filter to get this one, and you apply it multiple times to get a whole stack of these filters, feature maps. And then you might do pooling, and you repeat. So nonlinearity, and then you repeat, do again a convolution. Now, of course, this stack gets bigger because you apply the filter to each one of these, so you get a much longer stack now, and then you subsample again, such that the memory usage doesn't explode. In fact, some people believe that this subsampling actually also has a huge use in terms of becoming invariant to small deformations. Other people don't like them very much. And then in the very end, you just, all the pixels that you have, you stack into a big vector, and then you apply some kind of classifier to it, let's say simple MLP, to do your final classification. And clearly, when you do training, you go back through this whole process. You compute a loss of how well you're doing. You do basically chain rule to change the values of these filters here somewhere deep into the neural net. Okay. Okay, and this has actually been incredibly successful. Here's a few examples of how this can be successful. This is a dermatology example by a group at Stanford, where they took images of skin lesions, all sorts of images of skin lesions, and they took a neural network which is simply downloaded from Google that was trained on your vacation pictures and your family pictures, and then they slightly fine-tuned this model on the actual pictures that they were interested in, and they got state-of-the-art results. And then they compared that, so that's not incredibly sort of earth-shattering, but then what is really interesting about this is that they compared this to a whole bunch of dermatologists at Stanford Hospital, and what they found is the red dots here are, this is a sort of this sort of ROC type curve, and what they found is that the dermatologists, they did worse than the actual algorithm, except for this person here. But on average, they did worse for sure. These are, of course, very good doctors, and certainly, very willing to do their very best because they know they were competing with this machine, which is quite different from a doctor somewhere in the Midwest right after lunch, studying your images. I think it's a very convincing result. The result, of course, shows that when you stay in a limited domain, right, this domain is extremely well defined, and when you have enough data, in this case they had close to 130,000 images collected, then this deep learning works extremely well. But I'm not claiming, when you go from this to any other disease, that this thing works well, right? It completely breaks down. You have to retrain it, of course.
The precision of that comparison, did the dermatologists, the doctors, use also only the images of the lesions, or did they use?
I think.
Did they have access to more?
No, I think because no, I don't think so, because that would mean that they would have to have the patients there to study.
So they don't have the images.
So you think there might be other information around? You think a doctor typically might have additional information? Yeah, I don't know the answer to that. So I don't know the answer to that, but I would suspect they would have only the images to look at. And so a doctor maybe having more additional information like age or something like that, you could get better. Yeah, but of course a neural network could get better too, right? If it had access to that data.
This was supervised classification?
Yeah, it's very much supervised because they knew for each one of these what the class label was. Yeah. Yeah, it's transfer learning for a large degree. So this thing is, so that's somewhat of a surprise for the community, is that you could just take a neural network which is trained on a completely different task, on images which look completely different, like your pet and stuff like that. And then that is a pretty good feature extractor already. And then you can train something on top of it, and that gives you already pretty good performance. And then you can fine-tune the whole architecture, and that gives you even a little bit more better performance. But the fact that you can just have such a pre-trained network on a very, very large data set, and that works already very well, that's kind of interesting, that this transfer works so well.
Is it understood?
Well, what do you mean by understood, right? It's, there's no bound of some kind, isn't it?
Dermatology, some other branch of medicine? Is it just
Well, I think it's, people have intuition, but I don't think there is like a, I mean, analyzing these neural networks is extremely tough, clearly, right? So having some kind of generalization bound, I don't think we will ever get there anywhere soon. But yeah, so I guess people do have intuition somehow why this feature extraction already gives interesting sort of features that are, I mean, the first thing you do is, for instance, is for any image is basically edge extraction and corner extraction. And so the fact that you build up sort of these levels of abstraction, maybe it's only the last layers which really specialize in this particular task, right? And so if you retrain the last layers or chop off the last layers, then whatever comes here is actually already pretty good. People have done studies on precisely which layers contribute to this process. There's some old papers that look at that. Here's another example in pathology. So there is a huge number of these pathology slides. These slides are also very, very large. Like it's gigabytes for one of these. And it's very difficult to go through them. So it's not like you can look at them like this. You have to go through them like, with a moving sort of target. And so it's very time consuming. And so algorithms have been developed to detect cancer in these kinds of slides. This is tissue slides that are colored. So again, here is an algorithm which was downloaded. This is a Google Net. I think it's the same one as last time, maybe one version up, V3 or something. Again, downloaded and fine-tuned, and the algorithm got a lot better than the pathologists in this as well. Again, very well-defined task. And lots of data available to train. Okay, so I want to basically explain a convolution now as a message passing scheme, because I want to connect to graph neural nets in a minute. So a convolution, we can sort of think of it as a little filter that moves over the original image, and it takes the inner product of these filter values with the underlying pixel values. And then the inner product means that you add them up, and then you store the value at the next layer. Now you can think of that, and since you're doing this over multiple input feature maps, you can think of that as a message passing scheme, where this is your central node, and there is these neighboring nodes which are sitting here, and they have a feature vector, which is the value for that pixel, but then across all of the channels, all of the feature maps. So that's a vector. And then you multiply each one of your neighbors with a different matrix, and that's possible because you're always oriented like this. You know that there's a northwest neighbor, and there's a north neighbor, and there's a south neighbor, etc. So you can identify, these neighbors in this particular way. And you always multiply them with this matrix everywhere in the image, but different for each neighbor. and then you collect all of these messages, including a message from yourself, and you add them all up, and then you store the result in the next layer, maybe after you apply nonlinearity. So that's just a message passing scheme, right? So it's a different way to look at it, maybe. So that's how that looks on a graph, on a regular graph. So now the question is, what do you do if you have a very irregular graph, right? Now it's less clear what to do, because like first of all, so this node has 5 neighbors, but this node has 3 neighbors. And so how would you design a kernel which you would apply everywhere and which would be equally valid for 5 and 3 neighbors? The second thing is, if this is just one way to draw the graph, but I could have equally well moved this node all the way here. And I know it's a bit deceptive because this thing is planar and it just looks nice if it's planar, but it doesn't have to be a planar graph. But I could move this node anywhere else. And now the ordering would be screwed up as well, right? Which neighbor is where is sort of completely screwed up. And so I wouldn't be able, like in this case, to neatly figure out, okay, this is my north-west neighbor, and I need to sort of use this matrix to multiply it. So the only thing I can do is, if I want to be independent of that ordering that I choose, I need to use the same matrix W to multiply each one of the neighbors. Because if I use the same matrix W and I multiply them with each of the neighbors, then if I move this guy here, it doesn't matter because it gets multiplied by the same matrix anyway. Okay. So basically what we want is that if we permute the ordering in which I process these nodes, I'm giving my neighbors 1, 2, 3, 4, 5. If I change that, I permute that, then I still want, in the end, that the answer at the final layer will be the same. Should be independent of how I order my neighbors. In fact, what I want is that if I completely, let's say I give an order, a number to each one of my nodes, right? And I'm going to process this. I want that in the end, the result will be independent of that ordering, which basically means that if I permute to another ordering, I just permute all the results as well in the final layer. I'll make that more precise in a minute. Okay, so the simple algorithm back then that we developed that did that sort of had that sort of this invariance for treating the neighbors. So it treated all the neighbors the same, sort of an isotropic sort of assumption over your neighbors, has in fact a very simple update rule. So this is our graph convolution at point P, node P. There is this matrix K self which multiplies your own feature vector. And then there is this matrix K neighbor which multiplies the neighboring feature vectors and adds everything up to get this result, right? And then there's nonlinearities, etc. So pictorially, there's some input graph, and then every node collects neighbors or messages from the neighbors. So this node, let's say, connects messages from the neighbors, which get multiplied the same matrix their feature vector. You do this for every node, right? You push it through a nonlinearity, and then you repeat, and you do it again and again. And then in the end, you'll have sort of an embedding for every node in your graph. And sort of the input data now got embedded into some abstract semantic space. And then, of course, you might want to predict something about the entire molecule, so you might have to take this information, then stack it again, and then use it to classify something, like the property of that molecule. Is that clear? Yeah, so this and this are trained. These two matrices are trained. Yeah. Okay, so here's a simple example. So we take a CT scan of a lung. This is an actual example, and this might be interesting actually for the discussion we had for lunch, because this is a mean field approximation here as well that we sort of used. So we take a CT scan of a lung. We then do all sorts of local measurements to predict something about the probability that that pixel lies in an airway. So we're trying to segment sort of the airways of the image. And so we do all these local measurements of the probability that they're part of an airway, and also some local measurements, some local features that you compute. and we over-segment, so we basically connect every two neighbors in this graph that have a small chance of being on an airway, in an airway. And then we use a GCNN to clean up that image and only have the actual, airway edges left. And so we train that on about 30 images of airways. So it is pretty tough to train it because there's very little data involved. But then GNN doesn't need a lot of data in some sense. You could put a lot of data, but it doesn't have to be. And so we did a sort of a mean field version of this and a GNN, and we didn't actually do something that combines these two yet, but could be done. And this is the GNN result. This is the original one. This is the mean field one and the GNN. The learned one, which actually uses learning, does quite a bit better. Okay, so that was if you want equivariance under permutations, which is that the statement that if I label my nodes in an arbitrary way, I want the final result to be independent of that labeling. But you can extend that more generally to this concept of equivariance to say, okay, I have some function f that maps from x to y, which is, let's say, one layer in your convolutional neural net. And I have sort of symmetry transformations in x space and y space. So these could be a translation or a rotation or something else. And then I'm calling equivariant, sort of a map f equivariant, if I first apply f, which is the convolution, and then the symmetry transformation should be the same as first applying the symmetry transformation and then the map f. So in this case, if I have this image of a lizard, gecko, I do my convolution, I get this filtered image. I translate in this space, I get this image. I take a CNN, I get this filtered image. And then, of course, if I translate this, I need to get to that result. Now, in this case, the translation here and here are the same, but in general, this t does not necessarily have to be the same. It could be a more general sort of operation here on this image. And then you can ask yourself, why not make things invariant right from the get-go, right? So why do we insist on equivariance rather than invariance? So what is invariance? Invariance would be if this map here is the identity map. In some sense, whatever you get out here, this is just the identity transformation. Doesn't do anything. That's a complete invariance, an invariant map f. And the issue is that if you would be invariant, let's say after the first layer, you would do invariance. Then let's say I have eye detectors and nose detectors and head detectors and arm detectors and whatever. Then this would be a perfectly valid human being because I detect all these things, and since it's completely invariant to rotations and translation and all these things, it didn't matter whether the eye was detected here or here or here or here. It's just a bag of things that I detect. Where what you really want is to maintain the sort of spatial orientation or the pose of these things, right? I want to sort of say, well, I want the actual figure, I want to detect the actual figure, but then I don't care if this thing is rotated or translated, but the sort of the relationship between the parts should remain intact, at least for a while inside this neural net. At the very end, when I do classification, clearly, I want to be invariant. Because I want, if there is a true invariance, which means that a cat is still a cat if it's upside down, then I want the final classification to be invariant. So what are the reasons for equivariance? And so there's 3 reasons at least for this, but maybe more. So first of all, and you can see this very clearly in CNNs, you're doing a huge amount of sharing of parameters, right? If you take all the pixels of an image, which are maybe 1 million, and you use an MLP, you get 1 million squared parameters right there, right? But if you use a CNN, you might have, 9 per filter, maybe times 200, right? It's a huge reduction in the number of learnable parameters, which means that learning is far more efficient with your data. The second one is maybe more subtle, which is that it helps to detect patterns. It helps to stack the architecture, and that higher level neural networks can more easily detect patterns in the layer below. And one way to think about this is imagine that if you take an image and you shift it, and that the actual feature maps aren't shifted but are completely scrambled, then the next layer would have a very hard time detecting patterns, especially when they're local, right? And if this scrambling is completely non-local, then the next layer would have a very hard time detecting any patterns at the next layer. So it's kind of nice that if things, you know, transform nicely in your input space, that these transformations are also nice in every intermediate layer, because that makes it easier for the layer above to detect these patterns. And then the final one is sort of abstraction preserves symmetries, by which I mean if I do a sort of a transformation like a rotation, so this is pixel space, if I rotate a head and move in pixel space, if I take another head I also rotate, so these are sort of orbits of my sort of action of my of the group, the rotation group. Now if I do a feature map that sort of abstracts spaces into, say, one, you know, icon of a face, then we have sort of a contractive map. But the nice thing is that under rotation, you know, also whatever, you know, if this thing gets rotated, they would also map to the rotated abstracted face. So you can say that abstraction preserves symmetries, which is kind of a nice property to have. And I think there's some nice relationship to renormalization group here. People actually also study whether renormalization group procedures preserve symmetries, and that's a good thing typically. So I think there's at least some interesting connection there. Okay, so now I'm going to talk about some more recent work which has to do with sort of a new version of graph neural nets, so graph neural nets 2.0. And sort of the big brains behind this project are Pim de Haan, who is now a PhD student in Cuva Lab in Amsterdam, and also employee at Qualcomm, and Taco Cohen, employee at Qualcomm. And Taco Cohen has been instrumental in the development of this whole formulation of equivariance. So his thesis was about equivariance and how to apply equivariance in deep learning. So he has been, you know, very instrumental in this whole field. Okay, so let's first study what a GNN cannot do. What are the limitations of a GNN, right? So again, the GNN sends messages. So this node collects information from its neighbors and then processes it and then sends it on. And so in this case, since each neighbor gets treated exactly the same way, this situation cannot be sort of distinguished by this neural net, because it treats all the neighbors as a set, and the fact that they have some graph structure that is different in these two cases cannot be detected. So a graph neural net cannot see the difference between these two signals on a graph. It will process them exactly the same way, and that's a limitation.
But how is it possible? Because the two right ones, they are next to each other, and there will be also the messages to them and in between them, and in the two graphs, this will be different.
Okay, so let's see what we do, right? So this node, what does it do? It multiplies itself with a certain matrix. Fine, that's the same in two ways, no problem. And now it takes this and this and this and this, and it multiplies each one of them with the same matrix and then adds things up.
Yeah.
So here and here, it will give you exactly the same result.
Yes, but isn't it that then the other nodes in that graph would act the same way, that they would take their neighbors and send it?
No, I think so what we want is that this message that's being sent here should be different between this and this. And the reason is that, you know, this is actually a different input structure than this, because the underlying graph here, you know, looks like this, right? And these two are flipped, but that's not a symmetry of this graph. Oops. That's not a symmetry of this graph, right? So this is, I mean, if I tell you, can you tell the difference between this and this graph? You can say, yes, there's a difference, right? Because, you know.
Yes, I'm taking it more of an iterative procedure, and in the previous iteration, you know, the light blue one would be receiving a message from the other light blue one in the right-hand side, but not in the left-hand side, so that would kind of propagate. But maybe I'm thinking about it wrongly.
Well, first of all, there's supposed to be a lot more graph here that sort of sends information in here. And then at the next iteration, you know, you get the same phenomenon. So you get some pattern here that gets processed in the message that's being sent. So I guess I'm not quite sure how, at the next iteration, this can be corrected. But sorry?
Each neuron is going to send the information. So
Each
with the light blue sends the information to the light blue.
This one, yes.
But the other one,
Which one?
imagine that the light blue,
This
the,
one?
the one,
This.
yeah, sends the information to the next layer.
Oh, but that collects information from here, from its neighbors, right? That's going to go into here. But anything can happen, right? On this side, information flows into this graph, and you send some other information. I mean, it's very unlikely that in the end you're going to be correcting for the fact that you send a different message. You should have sent a different message, but you did send the same message in this case. So what do we really ask from a neural net? Right? If you go to the basics, what do we really ask from a graph neural net to be true? And basically what we're saying is that if I have this graph, and I have given some labeling to it, or I have some different graph. So this is Bob, and this is Alice, right? And Bob and Alice, find this graph with the labels attached, and they do their convolutions, right? Then we want that these two convolutions, since the original graph was exactly the same, they're isomorphic to each other, right? And actually the signal is also the same on both. The only thing that's different is that the actual labeling of these nodes is different. Well, it shouldn't. I mean, I should be able to remove the labeling and just do my convolutions in some sense. That's just there to put things in my computer. Now, what I want is that after convolution, that after Bob and Alice did their convolution, then the result should also be isomorphic to each other, right? So there should be a relabeling of this graph to this graph, which just maps this solution to this solution. Or in other words, if you just look at these things without all the labels, then it sort of makes perfect sense, right? Because, this thing and that thing are exactly the same. Does it make sense, or I see people frowning a little bit? So the symmetry of this thing is that if I permute the labels on my nodes, then I do my convolution, that should be the same as first doing the convolution and then permuting the labels of my nodes. So that sort of is the sort of commuting diagram that I need to satisfy. So the symmetry group is this group of all permutations of these nodes. Okay. So a GCN, or the graph neural net, is in fact equivariant because the features that we have here are simply scalar features. And now, if you just do some kind of message passing like this, I left out the self message here. You do some message passing like this, and you can convince yourself that the result of that doesn't depend on how you labeled these nodes, right? Because you just look at your neighbors, you send these messages, independent of how these things were ordered, you just send the same message, and then you get some result here. If somebody else got the same graph but relabeled it, maybe the ordering in which you got the result is different, but it's the same set of results that you got out. So there's also networks which are called global equivariant graph networks, where you just think of X as a vector, or even X as a tensor, which represents the entire graph, and you transform it as a linear structure with a matrix, or you conjugate it with a matrix. WX, W transpose, if this would be a tensor. Then, and then you ask, okay, if this is sort of the structure, what constraints should I apply to W for this permutation equivariance to hold? And there's a whole groups of people that have worked on this and analyzed this and found some very interesting results. The first result is, for instance, if you look at this as a tensor, the sort of the connectivity tensor with the features of the nodes on the diagonal, then you find that the most general kernel that you can write down has precisely 15 parameters, independent of the number of nodes. And that seems to be the Bell number of I think the Bell number of 4 or something like this. So anyway, there's some way that you can compute this, which is the tensor of order 2 going to tensor of order 2. You add those up, you get 4, and the Bell number of 4 is 15. And independent of the number of nodes, you get 15 parameters. So you get a kernel, you get 15 basis kernels. You can linearly combine those, and that's it. very interesting that that number doesn't depend on the number of nodes. Feels magical, but anyway. So every node has a representation in this way that is basically equal to the number of nodes in the graph. So this node has, because the graph has 4 nodes, has a 4-dimensional feature vector living here. And this node is a 4-dimensional feature vector. And so if I relabel the nodes, now I do not only permute sort of the particular feature vector, but I also sort of transform internally under the symmetry group. I also permute inside. And so the disadvantage of that is that you have order n squared things to move around. There's n nodes, there's n of these features, and they're all size n, and these operations are order n squared at least.
Something, so each node only has one attribute associated to it, right?
No, it's a feature vector, right? It's a feature vector. So this is actually a feature. Yeah. So for the G and N though, so it was in principle one number, but you can have many more of those, but then each one of them will be a scalar value. So for each one of them you will have this property. You can certainly have larger feature vectors, but they don't transform under the permutation group. They're scalar under the permutation group. These ones actually transform under the permutation group, because if things get transformed, then not only get they permuted, but they also get internally permuted, basically. Okay, so that is that. So now we're going to try to do something more general, and we're going to say, well, obviously we want equivariance under isomorphisms or relabelings of those nodes, because that's what we really require. The other thing is that we want locality. So this thing is not a local operation, because this multiplies a big matrix times a big vector. So we want things to look like message passing. We want local operations, because that scales a lot better. Right? I can certainly implement that sort of distributedly on a GPU or something like that. So we want to look things like message passing.
Not local, you were adding contribution from neighbors, right?
Well, okay, but not in this one here. Yeah, this one is a big matrix which multiplies x, and x is the stacked feature vectors of each one of the nodes. So
You can't put it at 4 with some.
yeah. This one is certainly local. So a GNN is a local operation, but it has the disadvantage that it treats all its neighbors the same, right? So this one doesn't do that, so it treats neighbors differently, but it's a global matrix multiplication. It gets very large if the graph gets very large, right? I mean, graphs of 1 million nodes, like contact tracing, right? You want like 1 million people in a country at least, right? That's a very small country. So if you have 1 million people, now you need 1 million squared matrix. This is impossible to run, right? So if you want things to scale, you don't want this. You want something that looks like local message passing, which means I only look at my local neighborhood, I collect messages from my local neighbors, and I do an update. But I don't want to treat all my neighbors the same. So that's sort of the tension that we have here that we need to resolve. Okay, so that's basically what I said, and then, yeah, okay, I already said all these things. Okay, so then comes the natural graph networks, which were developed by Pim and Taco, and I was also involved in this. And the natural graph networks looks like a message passing network. So it computes local things, but now the kernel depends on the structure of the local graph. So that's already different, right? So now you look at the local structure of the graph, and then you choose a kernel. And the kernel can be different for every local isomorphic graph structure. And it does look like a kernel that sort of multiplies a vector, but this is now all local. And this kernel also needs to be designed in a certain way such that this global permutation equivariance holds. And so the way things look like now is that, here's my little graph labeled in a certain way. So each node has a feature vector of the size of the local neighborhood, not of the entire graph, but only of the local neighborhood. So 1 has 2 neighbors, so it is itself and then 2 neighbors. 2 has 2 neighbors. 3 has 3 neighbors, so it's bigger, right? And 4 has 1 neighbor, so it's 2-dimensional, right? And if I now permute things, relabel things, not only do I permute the colors, but I also sort of permute the ordering of the colors inside the feature vector, which basically means that this thing should transform under permutation group of the local neighborhood.
Then you have one feature per edge instead of one feature per node.
Okay, we first have to define precisely what an edge is, but so we're going to send, let's say, a message from here to here, and this message is going to depend on all things which live in the neighborhood around it. So it will process basically, so when 3 sends messages to 4, it will take in this, and this information and multiply it through the kernel and then passes on the message to 4. So it looks at the entire local graph structure around it and has these kind of, these values and then imports these values and processes them through the kernel and then passes on the message. Does that answer your question? Okay, so as I said, every node has a feature vector depending on how many neighbors it has. And these feature vectors should transform under the permutation group. So in other words, if I relabel, so here's my little graph, this is sort of hanging off it. So if I have my little graph here, and now I change my labels, like here, then I should have that this feature vector here also transforms under that permutation group. It permutes the entries if I permute the labels of these things.
So it's the exact equivalent to the holonomy principle fiber bundle.
Yeah, and
Exactly.
yes,
The graph is manifold. You have a group here, which
Yeah.
is your
Yes.
propagation group. You have a fiber, and the condition you're
Yes.
asking exactly.
and
And you don't have holonomy yet.
yes,
Holonomy will tell you how that happens when you move on the path.
yes.
You'll see that
Yeah, we will get to that. I will not explain things in terms of fiber bundles, and I'm actually not qualified to use that language with any authority. But when you talk to Pim and Taco, they have that perspective on this, using fiber bundles and even using category theory, and there's a whole theory behind it.
That's a different thing. The
Yeah.
fiber bundle are more down to earth than that.
Well, for me, they're still far up ahead, but anyway. Okay, but anyway, you can think of this as basically the numbering on these nodes. You can think of that as your coordinates frame. So basically, it's the equivalent of saying, okay, so how do I orient my frame in some sense, right? So this is how do I, label my points, and that's arbitrary. The results shouldn't depend on how I choose that. But what I will need is precisely this fiber, I guess, transforming under the symmetry group of permutations. Okay, so now I'm going to introduce two conditions that we need in order to do convolutions. And the first one is, how do you deal with the symmetry? So let's say this graph here, so this is just hanging off there because to show that there is more. But this is our local neighborhood that we've chosen. So we need, we're going to send a message from P to Q, first of all. We're going to send a message from P to Q. And the local neighborhood of P is this here. Okay, so I have this feature vector living at P. Okay, and now, there is a symmetry in this graph, because if I relabel 2 and 4, if I say, this is 4 and this is 2, there's no way of telling the difference between those two. It's completely, I'm not supposed to look at this, right? Because I'm actually only considering this part of the graph. This is a symmetry of the graph, so whether I pick 2 or 4 or 4, 2, it's a symmetry. I will explain later why you actually need that, but now we're gonna say that we need a kernel constraint to take care of that symmetry. So basically, we can do a convolution first, which we send our message from P to Q. Q has a different coordinate system. And then basically we get from this to this result after we do our convolution. So we apply our kernel PQ, which depends on this graph structure, and we apply it to vector V. Now if we do our sort of symmetry transformation on our graph, this is, now this gets labeled 2 and this gets labeled 4. So you see that this node flips up here. So that is actually, that transforms clearly the feature vector. And we know how, because that's what I showed here, right? So this is how that transforms. Okay, so then, so now we have that. And now we need that if we do a convolution here, we get another result. We get this result. And what we need is that if we take this result and we apply the symmetry transformation again, we get back to this result. And you get some kernel constraint which looks like this. So this means that locally, if I have a graph with a particular symmetry, then I get the same result irrespective of how I happen to label these nodes. Okay, and that will give you a particular constraint on your kernel that looks like this. So now the kernel is not completely free, but it has sort of a constraint here, and it has sort of x values here and y values here.
Sorry to interrupt again, but
That's fine.
You're defining what's called a horizontal Laplacian
Okay.
because your convolution is an average,
Yes.
and this condition is negatively improbable.
A horizontal average. I'd like to follow up on this actually to make sure that we know. I mean, that might be open.
Understand, I'm just proposing it. It looks like
Yeah. Yeah. Alrighty. Okay, so then the next thing we need to make sure is that so this is parallel transport. You're probably going to tell me that there's this parallel transport on graphs. No, you should please say, because I learned from that too. That's great. So now actually, the next thing we need to say is that if there's two parts in the graph that are isomorphic, like subgraphs which are the same, then we want to share this kernel on those two places of the graph. So we need to transport this kernel to this other place in the graph. So here is our original message again that we are sending. Now here's another another graph somewhere else, maybe a subgraph somewhere else in the graph, or a different graph or whatever. Right? That's isomorphic. At least this local part is isomorphic. Now, of course, I have a different frame here because I've labeled it in an arbitrary way. So I have some transformation that does the relabeling for me. So I get again this. And then if I do my convolution here and I do this isomorphism transformation here, or I do the convolution here directly, I should get again the same result. So this should map to this result. And this is basically expressing a weight sharing constraint. So it basically means that the kernel I'm using at PQ is the same as the kernel I use at P prime Q prime, except for the fact that I've used different coordinate frames on both sides. So I should compensate for the coordinate frames, basically. I should transform to the same basis as the other one. Okay, so then you get this kernel constraint. It's not a kernel constraint, but it's in a way a sharing constraint. How do I share a kernel in one part of the graph with a kernel, in the other part of the graph? Okay, so this is my explanation of, just to get some intuition of why these two constraints, we need to sort of use these two constraints in order to get this global equivariance. And sort of in the Netherlands we get told stories when we're young, which are called Jip and Janneke. And it basically, when you say explain something in Jip and Janneke language, it means try to make it as simple as possible. So that's what I'm trying to do here. So what we need is, so basically we think of Jip and Janneke, they both have a graph, and the two graphs are isomorphic. But they don't know, right? So they just have some graph, they have slammed on some labels on each of the nodes, and they're both going to do a convolution. And the signal on the graph, the initial signal is also the same. Okay, so then the procedure is as follows. They first go to, they select a local sub-neighborhood around the edge that they're going to send the message, and they're going to go to the library to find the graph that's isomorphic to that neighborhood that they found. And it involves, and they also grab the kernel that belongs to that part of the graph, right? But of course the kernel has an arbitrary labeling, so they need to sort of compensate for the labeling, which is a simple transformation. So both do the kernel transformation using the same kernel, but only in a different frame. So then, I guess they have to map to the canonical labels of the frame that they get, right? So the graph that they get, it has a canonical labeling, and they have to map to, they have their own labels, they have to map it to the labels of that canonical labeling of the graph. The problem comes when there is a symmetry. If the graph has a symmetry, you don't know how to map your labels to the labels of the graph, because you could have done it this way or this way, and it would be exactly the same. So they have to pick one, but since our procedure was equivariant under that permutation group, everything will be fine in the end, right? They just get the same result, but maybe permuted. So they both perform all their convolutions internal on all the subgraphs, and then in the end they get the result, and they find that the result is a permutation of each other, because they've been using the same kernels but just permuted variants of it. And I guess the upshot, which is really important here, is that the natural graph neural net is not isotropic. So it treats neighbors differently. Like the graph neural net actually treats the neighbors the same, this procedure treats the neighbors differently. Okay, so that's that part. I'm not sure how far I am with my time. What is the?
You still have half an hour.
Okay. Okay, so let me keep on going then a little bit. So that was graph symmetries, which were permutations. But you can also look at other symmetries. For instance, this is a lung nodule detection. This is skin lesion detection. This is pathology slides. Clearly, it doesn't matter if I rotate that image. The answer of my classifier should still give me the same result. And in fact, so this is a very old, it's a little movie by Jan LeCun, where if you take your digit and you look at your feature maps, and you see that this equivariance of this feature maps, it works out, right? I mean, you move, the feature maps get translated if you translate the input. But if you rotate, it's not the case, right? If you rotate, you see this thing actually changing. And the same thing happens here. There is some, if you rotate this input map and then you stabilize it by sort of using a rotated camera, you see that this actually changes if you rotate, where what you really want is something that is not changing or equivariantly changing. Okay, so so the question becomes, how do we define a convolution which is not just for translations but also for other group operations or group actions? So you can think of a convolution under translations as you have a function, you apply a translation operator that gives you fx minus s, right, which just moves the image. And then a convolution is you have a feature map, you apply your translation operator to the feature map, which moves this somewhere in the image. You do your inner product, of the feature, the translated feature, with the underlying image, and then you get your result, which is and then you sum over all these things and you get the result. Now that generalizes very easily if you take another thing like a rotation. So here you say there's an operator which acts on f as a rotation, which is f of r inverse of x. That operation looks like this. And then exactly the same, you would apply, instead of a translation operator, a rotation operator to your feature map, and again apply it on all orientations of your group, and then do the inner product and sum things up, and then you get your group convolution. If you don't like equations but pictures, here's the picture. So here is your feature map. It's basically an edge detector. So if I move my this bar and I do my convolution, I get basically this nice equivariant structure. If I do, on the rotations, then this is what happens, right? If I rotate it around and I get these response from my filter, and that's not nice equivariate. So the group convolution, so that Taco Cohen invented in 2016, actually there was also Sander Dieleman at DeepMind that also at the same year had a paper which was very, very similar. So it generalized this convolution to a a rotation convolution under 4 orientations of 90 degrees rotations. Right? So it's very simple. You take your filter, you slide it over the window in a particular orientation, you store the results here, and then once you're done, you rotate your filter, and then you do it again, and you store it at the next layer. So now you get 4 feature maps instead of 1, and Jeff Hinton calls that a capsule. Right? So those 4 feature maps now make up one capsule. And you can see that if you under rotations, you sort of permute, cyclically permute through these capsules. And that's shown here. If my input image is like this, I do my convolution. Now let's say I have an eye in a mouse detector, right? But since I do them at 4 different orientations, I have sort of 4 of these. Each one comprises one of these feature maps. Then at this particular orientation, I get these responses and nothing in these feature maps. But if I rotate the image, I get these responses, which are rotated themselves, but also I've shifted to the next feature maps. So instead of these feature maps, now these feature maps get activated. So the action of the rotation on the feature maps is slightly more complicated than on the original image, which is just rotating the pixels. It rotates the pixels, or the activations, but it also cyclically permutes through the feature maps. So that's the action phi y, a long time ago that I showed, right? The action in the space of feature maps. So here's maybe an example to show this. So if I take an RGB, image, right, and I rotate it, right? So the question is, does this comprise a sort of 3 scalar fields, or is this one vector field, right? That's the question you can ask yourself. You can think about this for a second. What does it mean when something is a vector under rotation? It would mean that, let's say, these pixels start to interact, right? So a pixel value here would depend on the pixel values of the underlying images as well. If it's scalar, it would only depend on the pixels inside one of these maps. So clearly, in this case, I can build this out of this by just rotating the pixels. I don't need these pixels to build this pixel. So it's 3 scalars. And so the representation basically would be 3 times the identity here. So you would rotate, but you would keep you would not mix the 3 channels. Now if you take the derivative map, which looks like this, now so if you take a rotation and then the derivative, or a derivative and then the rotation, now these are vectors, and this is a vector, and this is a vector, a 2-dimensional vector, and there's 3 vectors of length 2 basically in this representation. So you get a representation which is 2-dimensional, and it internally, the feature maps, the red feature maps internally rotate into each other like this. So more generally, for steerable CNNs, what you get is capsules where you have internal representations, typically irreducible representations of the group that transform this capsule, but don't mix between these 2 capsules. So these, so you basically form these sort of capsules which form irreducible representations of your group. And here's sort of an example of how that works. Here's the input data, which is sort of a rotating image of a table, and then you can then stabilize it. Basically, you can imagine that you then look at the feature maps, and then apply the inverse transformation that you applied here, and see whether then this thing doesn't change anymore. And clearly, it's completely stable here, so it's invariant. And here, or equivariant. And here you actually have vector fields, which are not just scalar feature maps, but more complicated capsules of higher dimension, and they also are equivariant under this work. Okay. How much time? Yeah. Okay. We keep going. So then, the third category of things I want to talk about is then sort of deep learning on manifolds. And so you can imagine that you want to sort of analyze an image of a body like scanned, and you want to figure out maybe where the legs are and where the hands are, or you want to actually equate for 2 different images, what are the corresponding pixels. Or you can think of a drone that's looking around in the world and that's sort of projecting the world on a sphere around it. And clearly, if the drone is moving around, the world, it's like in the internal frame of the drone, it's like the world is turning around on the inside of the sphere. And so the question is, how do you do learning on these sort of manifolds? And this is actually interestingly related to general relativity, as it is. Actually, I wrote my thesis a long time ago on this, and this was the picture on front of it, which says that if you take an incoming particle or an incoming light ray and here are 3 particles, then the way to construct gravity in this world is to basically cut out pieces from this world and identify the edges. And so basically a particle or light ray would come in here, would find the point where it's identified, but in the meantime, because an edge was removed, it has bended and it would go this way. But it's kind of a topological theory of gravity. And that's exactly, this phenomenon is exactly the same phenomenon that we will use. So here's maybe written out the problem that you have if you try to do deep learning on a curved manifold. In a flat space, you take your kernel and you translate it to some other place, and it doesn't matter which path you took, right? It could have taken any path, and the parallel transport is independent of the path you took. So it's well defined how you move your kernel from here to here. Now, if you're on a curved manifold like this one, there is an angle, all the curvature is kind of concentrated on these points, because everything else is flat, because you can sort of unroll this cube like this, right? And it's flat everywhere, except for the fact that you have certain identifications. So these 2 edges are identified, right? So if I send in a light ray like this, it goes here, and it finds the identical point here, and then it moves this way out, right? And so if I get my kernel and I transport it, it goes here, and then it gets 90 degrees turned. In other words, if I go through this path or this path, my kernel is turned by 90 degrees. So that is the problem, that you don't really know how to transport your kernel from one place to the other place. Put another way, similar to the labeling problem, you have to pick some frame, some local frame in which you define things, but then the orientation of the frame should not impact the final result, right? So you should be equivariant to which frame you precisely took. And this is again fiber bundles, actually, same thing, yes. Yes, yeah, that's clearly a holonomial, right? This is the definition of a holonomial, basically.
Could you explain the fact that the kernel rotates?
Sorry?
Could you explain the fact that the kernel rotates? When you move it?
Oh, maybe we can try here with this graph. So, so here's a kernel, and you have to try to do parallel transport here on this. Actually, it's easy. It's better here. So you have to define parallel transport on these 2 paths, right? So of course on this face it's easy, right? You know how to parallel transport a kernel. You just move it. But then you get here. But in fact, this is flat. There's nothing curved about this thing. It looks curved, but it isn't, because you can unwrap it and it's just, flat. So you just move it as you think you would have to move, parallel, So basically when you arrive here, it's still up, right? You do the same thing along this path, but then when you go this way, these things are rotated. It's like magic, right? As a magician, you think, locally you think nothing's wrong, nothing's wrong, nothing's wrong, nothing's wrong, and then you get together and then, damn, rotated 90 degrees. Right? And I guess you could see it here too. If you unwrap it, it's basically, this is the same as this, except for that you need to identify these lines here. But there's this angle deficit, which means that if I go in like this, I go out like this. Yeah. Okay, so basically on the sphere, you get some problem with the orientation of your frame. The orientation of the frame is undefined. So you have to pick some frame, and then you have to do your computations in that frame. But you have to realize that the final result cannot depend on what frame you picked, because there is no globally unique frame that you can easily pick. Well, not on a sphere, but there's topological reasons why you cannot do it. But anyway, we formulate it in such a way that we don't worry about it, and we can sort of treat this frame as a gauge, and we want to be independent of that gauge. There's a choice of coordinates. And in a similar way, by the way, in linear algebra, you also pick a basis, right? And you write down all your things in numbers, but that's already assuming a basis. You should be able to transform to a different basis. All your numbers will change, but in the end, the result should be exactly the same, right? If you choose one basis and I choose another one, and we do our computations, and then we compare notes, we say, oh, we have very different numbers. But then you say, well, if you would transform to my basis, then all the numbers are exactly the same. There's no difference here. And for a Möbius strip, it's basically a mirror transformation. Okay, so then what I want to talk about is sort of a version of this that is on meshes. Actually, it's interesting that we just looked at spherical CNNs, and in this paper, actually, Mario was a co-author. He's doing calculations, but yeah. So he is. This one is. He was a co-author on this paper. So, okay. So what I want to talk about now is so equivariance messiness. So how are we going to do convolutions on these curved objects? We did have a paper which looked at the continuous case, but that's not very practical. So we want to turn this into a practical tool. And so how do we do our convolutions on a mesh? So we first build a mesh on on the curved object, and then we're going to do convolutions on this meshed object, so basically on the edges and the nodes of this graph. It's similar to a graph neural net, but it's not the same as a graph neural net. I think I want to really emphasize that. People have done these things, but then with graph neural nets. But the problem is that a graph neural net treats all your neighbors the same, as I explained before, and that's suboptimal. In fact, it doesn't take care, it doesn't know about the actual geometry of the underlying surface. Okay, so how are we going to do this? Well, let's take some kind of meshed sort of part of an object, and we want to send messages from these nodes to the central node, like in a graph neural net. But we want to do it in a way such that this one and this situation are different, because these are two different geometries, right? They look different, basically this angle is different from this angle. So we want a procedure that recognizes that these two situations are actually different, and that's what we're going to try to do. So here is sort of the equivariant mesh neural net, if you want. So here's my curved object. Here's my point P, and I'm going to collect information from these neighbors. Now, in order to do that, I'm going to first pick a gauge. So I'm first going to define this tangent plane here. And in this tangent plane right here, I need to pick a gauge which is, what is my orientation 0? What does 0 degrees mean? And this is completely arbitrary. Everyone can pick a different, sort of reference angle. And so this person took the green dot as 0 degrees, and this person took the red dot as 0 degrees. And so then this person does a convolution, and this is just scalar convolution, got this result. This person did this convolution using the same kernel, right? The same kernel got this result, and we just need to understand how this transforms into this. Now this is a scalar field, so in this case these two are actually exactly the same, so no worries. But what if it would be a vector field? So in this case, in this gauge, let's say, I would take as output a vector, and it would be oriented in this way. And in this gauge, I would get a vector, and it would be oriented in this way. And now these two things are actually the same, but expressed in different bases. So I just need to understand, how do I transform this back into this, which is just another rotation. And as long as I know how to transform the results into each other, I'm fine, basically. I'm independent of the actual orientation that I picked. Okay, and that actually means that you're going to apply a constraint on your kernel that looks like this. Okay, so maybe I'll skip. No, maybe not. So, okay, so maybe look at this picture. So how are we going to do the parallel transport? So we're going to have our local reference frame, which our tangent plane. Sorry, our tangent plane looks like this here, this circle. And of course, I have chosen an arbitrary frame here, so some reference frame. And now I need to parallel transport it to here. So I first need to align this tangent plane to this tangent plane, which means that I just sort of rotate it over so that it becomes this. This is my first transformation. Then I can easily transport it to this plane, because now these two things are comparable. And then this person and this person had different frames again, so I need to also transform from this frame to this frame. And all of that is stuck in this matrix rho, which is the parallel transporter. So how does the actual sort of mesh neural net look like? So first look at the graph neural net again. So the graph neural net had one matrix multiplying all the neighbors, and summing, and one matrix for yourself. Now the mesh neural net is slightly more different, more complicated, but not much. So we have this sort of row which we can pre-compute, which takes care of the parallel transport on a curved manifold, as well as the fact that we have different frames. That's going in here. This is our parallel transporter. So now we parallel transport F to P, so FQ to FP. So now it's living in this frame. I do this for all my neighbors. Then I use my kernel, which now depends on angles, and I add them all up, and I multiply by this guy, and then that's how my convolution is defined. The most important part being that this now actually can depend on an angle, and it's no longer isotropic. Okay, so that's sort of, I mean, this is a whole new can of worms that I would open up. So I don't know if there's questions.
Yeah, we could ask 2 questions.
Yeah.
So maybe let's open to discussion. I mean, unless you want to share.
Well, I can quickly go over this. I don't know. People can choose what they want. They can hear about this, or they can ask questions. It's up to you.
Are there some questions, like in higher level about what? So was related to you?
I guess the take-home messages are that graph neural nets. If you deal with a graph neural net is a fairly limited solution. You can do better. If it's a graph, you can use this natural graph networks, which is already more powerful. If you're on a manifold, if it's really a mesh on a manifold, you can use this mesh CNN, which is also more powerful in the sense that it allows you to not be isotropic with respect to your neighbors. The details maybe you can read up as well.
Like maybe one question, like what would be, say, see when we are looking at the supervised learning, everybody's like testing on, say, Cypher and ImageNet, and that's kind of the standard cases on which you want to compare your method. And now you described a nice set of methods, and you're kind of saying conceptually why one is better than another. But do we have some kind of like a standardized benchmarks on which we could be basically comparing one to another?
You're gonna not like my answer, but it's a spherical MNIST. They have an MNIST for everything. So they basically, you can wrap MNIST on a sphere or something like this, or you can wrap MNIST on a manifold. But there's also other things, right? So there's also like 3D data for like if you have like a depth data for inside of a room, right? So you might have 3D data, and you can try to do sort of 3D convolutions on that, or you could look at Earth data. So we actually have a data set of storms on the Earth. You could try to predict when and where storms will appear by doing convolutions on spheres. There's many, on the graphs. Clearly, there is a lot of.
I was thinking
yeah.
of the graph. I mean, as you're saying, on the sphere, yeah, if you are in astronomy, yeah, I could imagine like a lot of. But I was more thinking of the graphs.
Well, there is a ton of graphs, right? I mean, what I think the one that I like most is predicting properties of, of molecules is one clear one, right? But also, in chip design, you typically have what's called a netlist, and a netlist is a big graph which tells you precisely which small little component interacts or needs to send information to which other little component, and then you need to put all of these things on a two-dimensional plane because that's your chip, right? And so you may want to learn some kind of function on that graph that predicts something about how successful you'll be of putting things on. There's a ton of things. I mean, there's so much data that comes in either sets or graphs.
Yeah, I mean, sure, but I was more thinking like, what is, if you want to persuade one of your colleagues that your method is better than theirs, like you just pick one of those datasets, or is there a standardized kind of one?
Well, for molecules, there certainly are standardized data sets. I forgot what I call GM3 or something like this. There's some standardized benchmarks on predicting properties on molecules. So there's certainly those things. There's also in this sort of world here. Oops. In this world, I think it's called Faust data, and there's a whole lot of tasks that people try to solve on these kind of meshed sort of body poses that you can work with. In medical imaging, clearly there's a lot of these meshed networks that you may want to predict something about, you know, heart disease by just looking at how a heart beats over time or something like this.
So I also have a question. So the example with the graphical network was just basically looking at the, you know, full permutation symmetry. Right? This one seems to be more
Yeah.
discretizing some, let's say, smooth manifold in
Yeah.
3 dimensions, and somehow the equivariance that you're trying to build in is, you know, with respect to, let's say, local angle
Yeah.
transformations. But what if you had, let's say, some, let's say, graph which has some, you know, which has, let's say, some arbitrary symmetries,
Yeah.
which, for example, are not even necessarily local, so it's not something, you know, could you build some arbitrary sensitivity, or equivariance with respect
Yeah.
to some arbitrary symmetry into your framework?
Yeah, absolutely. So actually we applied the work, I guess this work on an icosahedron. So an icosahedron has it's a global symmetry where you can sort of rotate over certain angles, right? And you know, you can build a neural net that is precisely equivariant under these sort of discrete set of transformations. Yeah. So that's a global symmetry. Then you can also think about more local symmetries. But that's more like in the graph case or in the here, right, where you can sort of think about more local symmetries maybe. But yeah, yeah.
But right now you're building in the symmetry at, you know, at the very beginning in the construction
Yeah.
of the network. Would it be possible to, you know, try to infer in some way what the symmetry in data is, and sort of try to do it, you know, on the go somehow?
Yeah, that's a holy grail, I would say. So first of all, groups is a very limited set of transformations. There's semi-groups, but then there's also, you know, transformations which are not necessarily groups or semi-groups, and still you may want to build some kind of, well, I would say equivariance or approximate equivariance under these sets of transformations. And why, you know, we're working on that, and why I'm inspired by that is because in the brain this actually seems to happen, right? I mean, we have topography everywhere in our brains. So certainly under rotations, we have sort of these columns, these orientation columns, and there's a ton of these things happening. And so somehow your brain figures it out in an approximate way.
So why wouldn't that be a group?
Well, rotation clearly is a group,
No,
but
whatever your brain,
yeah,
the
but
actions of a group for the brain seem obvious.
yeah, you know,
This and that or that. And
yeah, but there's also other things like there's lighting changes and ocular dominance. There's a whole bunch of transformations that are not necessarily a group. You know, like a scaling, for instance. If you pixelate the world and you scale, it's no longer a group; it's a semi-group. So yeah, so or yeah. So anyway, so I would think you're encountering a lot of transformations during your lifetime, and you realize that the world doesn't change under those transformations, right? If you turn down the light, then I'm not going to interpret everything differently. And my interpretation is exactly the same. I compensate it away. So anytime I do something like that, even it would be a color change or whatever it is, I would say your brain somehow builds some kind of smoothness around it, some topography around it. So it basically says, well, if that happens, then in my representation space, it just shift smoothly. I don't jump to some completely different place, but I just shift smoothly, right? And there's probably a function for that. Maybe, you know, the next layer needs to be able to interpret what's happening in a nice way. And for that, it's not very nice that if you have some module that tries to detect something, and something changes a little bit, and then somewhere, you know, in some other part of your brain, you know, things become active, then, you know, it's not very easy to learn this, to stack this, right? So there's probably good reasons for the brain to include this smoothness under these sort of transformations. I think groups are very nice because you can put all the math in and all these kinds of things, and graphs in particular are very, you know, clean objects. But the world is more, you know, complicated, I think, and so I think it's a very good idea to try to figure out if you can learn these things on the fly, if you can just expose an AI agent to the world, and all sorts of transformations are happening, and it should somehow have this notion of constancy, that the world doesn't change very quickly, actually, even though things might change quickly on your retina. And if I rotate my head, things dramatically change in terms of the representation, but the world doesn't change. And that knowledge probably is built into your brain, and it gives rise to these kinds of representations somehow.
I have another question. Could you tell us, what's the main advantage of building the symmetry into the network with respect to augmenting the data, if you know the symmetry?
Yeah.
I mean, is it just the speed that you just end up with a smaller data set and fewer weights, or is there some other interesting?
Well, first of all, you don't have to learn what you already know, right? So this should be a golden rule, which is if you know something about the world, you should put it in your model and try not to learn it, because that would give you, in some sense, capacity to learn other things. Of course, you could argue, well, I'm expanding my data set, and therefore I will get more data, but yeah, I argue that it still takes time to learn it, right? Maybe you can expand your data set like by doing all these augmentations, but it's imprecise, first of all. You have to learn it, and it takes time to learn it, and you might learn imprecise relations where you know the relation very precisely. So why not just bake it in? In fact, we did all the experiments, and the experiments show that if you do equivariance, it is actually better than if you do a data augmentation.
Like faster or
No, actually accuracy is higher. I mean, if I give you a data set, and either you build an equivariant net or you do data augmentation, you get that equivariance is better than data augmentation, and equivariance plus data augmentation is better than both.
Oh, okay.
Yeah, so it also seems to happen, work a little bit independently, strangely as well. But,
When you do this equivariant thing, you have to choose this kappa, the kernel, whatever you call it.
yeah.
Is there a good choice? Do you know how to choose?
Oh, we learn it, right? We learn this thing.
You start from whatever?
Well, the initialization is hopefully not a huge issue, but typically it is a bit of an issue, I guess. But yeah, so so for instance, here's a kappa. Now there's some constraints that come from the equivariance that you put in, and of course there's some sharing constraint. But these numbers, x, y, and z are still free numbers to learn, and you just learn them by backpropagation through this network. Of course, you do layer after layer of this, right? You do this, nonlinearity, layer, nonlinearity, etc.
So if I understand the way we perceive depthness or 3D, or 3 dimensions, is because we have 2 different images with slightly different angles.
Oh, the reason we see depth, you mean?
Yeah. Or 3D, like, there's information.
Well, there's also, there's not just depth, there's also the fact that we understand the world, right? I understand how this thing works, so I understand that somebody is sitting behind you, because that person you're occluding that person. So I know you're before that person, and that means that in my brain I can sort of put these things at different distances.
So all that comes from just 2 images, right? You're looking at 2 slightly different
No, I think you can do depth perception with 1 image.
I don't think it's again if you say both, right? Because you have like when you have this ophthalmology exam, they give you these pictures that just look like random noise, but if you stare at it actually correctly with the Schweizer, you see like a 3D object coming from it, and they check whether it's right and
it's
it's probably both.
Yeah, it's both. I agree. It's
other information to guess what you see.
No, it's 100% certain both, right? I mean, it's not that the brain wouldn't use it. It's clear that you use depth perception, but it's not the only thing. You can actually learn depth from a single image, but you will have to know a depth map. So in some sense, if you know you can use supervised learning. But I think we are kind of inborn, when we were born, we have sort of a notion of how the world works. And we can probably use that already to understand something about what's behind something else and stuff like that. No. It's time, I guess.